Danny?
Nope. Stop. I just
Stop?
skipped it. Yeah.
What can you do? Okay. I feel bad for the people that couldn't make it. Okay. So that sulfur would gain a negative charge now, so we're going to draw the pair over here. Okay, so we have an acid-base pairing always. So this is going to be our conjugate base on the other side. Conjugate base. And all we're going to do is draw the same thing, but given that the proton was abstracted, and now the sulfur gains that lone pair, and it has a minus charge. Okay? And then we say that the base gained that proton, so we're going to draw it. So it still has one lone pair that was untouched, but the other one gains like that. So now we have 3 bonds to nitrogen with 1 lone pair. So that means that you have 1, 2, 3, 4, 5. So it has a neutral charge. Okay. So this is the base, and that means over here, that must be an acid or base? Acid. Acid. So this is our conjugate acid. These are paired with each other, okay? So when we're talking about equilibrium, it all goes down to stability. Everything comes down to charge and stability. So
a lot of people are asking about what happened to the sodium.
Yes, so sodium is a spectator ion, so you really don't have to care about it. It's just a spectator. But if you wanted to put it, they don't expect you to put, like, I'll check the key. They put in the key, but you would not get points off. And if you do, like, talk to me, I'll talk to them. But you could put it there, it would stabilize now the negative charge on the sulfur. Okay? But since it's a spectator, it's not important because that's not the products that we're forming. Does that make sense?
So can you use the spectator ion to determine what's your base? Or
in a sense, yes, because your base is going to have that minus charge on it. That makes it more basic because it's so unstable. So the fact that it has that spectator ion next to it means that the spectator is balancing out or neutralizing the negative charges on the base. Yeah. So if you were confused and you weren't sure, like, yeah, resort to that, sure.
Can you explain the arrows on the top?
Yes. So when you're showing the movement of electrons, you always want to move the electrons. You don't want to move the atom. So if I were to have put the hydrogen moving towards the electron pair, that would be incorrect. Okay, so I circled the lone pair. You don't have to circle it, but just to show you guys, I like to. And you show it going towards the hydrogen, it grabs the hydrogen, and that is now the bond that has been formed right here. You see, I'm trying to highlight it. You see it? That is the bond that has been formed right there, okay? And then that means that the bond between the sulfur and the hydrogen broke, and it gained the minus charge because that bond, you can't really see it, but it went here. It broke. And so it gained those 2 electrons that was in the bond is now belonging to the sulfur, so that's what gives the sulfur the minus charge. Does that make sense?
What about the equilibrium here?
That's what we're going to do now. So that's what we have to do. All right, but any more questions before we get to that? On top of the sulfur, yes it is. You can't see it, sorry. Right there. It is. That's what's giving it the minus charge. Okay, so now we have to address the equilibrium and where it's going to lie. So this is very similar to the question that we did up here in the sense that we're talking about stability of the conjugate bases. Because you cannot compare things that are neutral. We're using the bases, so this one right here, and the conjugate base over here. We're using those because they have the charge, and we're going to compare them in terms of their stability, okay? So whichever one we determine to be more stable is the one that the equilibrium will lie towards. Equilibrium lies towards stability, okay? That's really key. So how do we compare this? We have minus charge. Let's write the cardio off here. We have the minus charge on nitrogen and minus charge on sulfur. Okay? So of course they both have charge, minus charge. And so we're moving on to the atom. So the atom is going to include 2 things. The electronegativity in addition to the size. Okay? I'm going to put size first for a reason. And within electronegativity. Okay. I want to go to a periodic table. I think I saved one.
I got one.
You got one? I would not be able to. Yeah, thank you though. I just want everyone to see it. Thank you. Okay, so this here is the trend of electronegativity as we go up and to the right. You see it gets more electronegative. So we're comparing, remember in our question, we're comparing the minus charge on the oxygen versus minus charge on sulfur. Okay, so you're probably going to look at this and you're going to say, so the oxygen is more electronegative, so it's probably more stable with the minus charge. Okay, we can only use that trend. I wish I could write on this.
You can. If you go to
Edit?
markup,
Yes.
the 3 dots.
Mark? Yes, thank you. So you can only use that trend when you're comparing things that are in the same period, okay? Because the electronegativity increases as you go to the right. Okay? But if you're comparing things, for example, in our question, we're comparing sulfur to oxygen. So oxygen does have a higher electronegativity. However,
Nitrogen.
or nitrogen, sorry, but it goes both ways. Yes. So our question is talking about nitrogen, but let's say our question was OH minus, right? Same idea. So the nitrogen is more electronegative. However, our trend of size goes this way. The more you go this way and down, it becomes bigger. The radius of the atom becomes bigger. So you're delocalizing a negative charge over a greater area. So the greater the area, the more delocalization of a negative charge, the more stable. So which one would be more stable with the negative charge? Nitrogen or sulfur, given that rule of size? Sulfur. It would be the sulfur.
So size is, in this case, is 1 and 1 and 1.
Exactly. So remember how we were comparing in a previous question carbon with a minus charge to oxygen, right? So notice how carbon and oxygen are on the same period, right? That's why you can use that rule of electronegativity to compare them. The size doesn't differ that much because they're in the same. So oxygen was more electronegative, so it can carry that negative charge, yeah. I think I saw a hand over there. No? Okay, so we determined that the sulfur has a higher radius, bigger radius, delocalizes the electrons more. I hope it doesn't remove everything. Okay. So as a result, the sulfur is more stable with the negative charge, so I'm going to put more stable. So if this is more stable, which way does equilibrium lie?
To the right.
To the right, towards stability. So we put the arrow going to the right in the box. Okay, any questions about that? Yes.
So, because the sulfur anion is larger than the nitrogen, that means it's more stable with a negative charge than nitrogen is. That would also make it the weaker acid.
It would make it, so you're talking about like this over here?
The weaker base, I'm sorry. That's
The weaker, yes, the weaker base, exactly. So you're talking about this right here. This is a weaker base because it's more stable.
Because we're supposed to.
Yeah, so the how do we say it? Like, if you have a friend that's really basic, they're really unstable.
Oh.
You use that. The hell stable. Yeah, so the more basic something is, the more unstable it is because it wants to react with something else in order to become more stable. Does that make sense? Yeah. Okay, I think we got his question answered. Any other questions about that? No? Okay. So we're going to move on to everyone's favorite.
No.
Resonance. Okay, so let's read this. So for the structure given below, draw the important resonance contributors and circle the major contributors. Okay. So something that's really key is that whenever you have a positive charge, right, and a double bond adjacent to it, you're going to want to show one arrow of movement, like this. Boom. And then where does the positive charge go? It would go to the carbon that lost that electron, that lost part of the bond. So the positive charge would go to that carbon that I kind of showed the arrow for, okay? Or better, let me highlight it, okay? It would go there. So one arrow, commonly when you're doing positive charges, and with negative charges, you're going to start with a lone pair somewhere, and you're going to use the lone pair in order to propagate something else to move. So you want to have a pi bond adjacent to that lone pair. So this would move here, and where would this move? Boom, onto the carbon. So you're pushing it. So this right here, there are pi orbitals there, pi electrons, and so that's what the lone pair is moving, okay? So 2 arrows commonly with the negative charge, 1 arrow commonly with the positive charge, okay? So you need to think as the, let's start off with the positive charge, okay? Well, that's all we have, but you need to think of it as this right here, the adjacent pi bond, is like a door hinge that is swinging towards the positive charge. It swings like that, okay? And when we do resonance, we'll draw double-headed arrows. We can include this one too. You just draw everything else the same, and then you look at what you moved. Okay? So we move this guy up, so the double bond goes here, and then where does the positive charge go? To the carbon that lost those electrons, okay? So that would be our first one. And then we have to make sure to bring everything else down. Like nothing happened to that pi bond, okay? Can you guys see it? Yeah. Okay, so then we'll do another structure, and you can indicate in different colors. I'll do it in different colors, but on my exams, I would always put like A, B, because I had the same colors. That's all. So now what we're going to do is we can use the resonance structure that we just drew in order to draw another one. So we can move this like a door hinge up, get rid of that positive charge, and displace it somewhere else. So let's draw this one. So it's kind of going down to the bottom, but I hope you can still see it. So that's where the pi bond now went. You have a pi bond here, and then their positive charge was displaced onto that carbon. Does everyone see that? Okay, so we cannot move that positive charge anymore if you're looking at this structure. Okay, it is too far away from the pi bond that is right here. I don't know if you guys can see that, but it is too far away from that pi bond at the top in the blue structure, so you cannot rotate it anymore, okay? So you kind of use everything up that you can for now. Okay. So no other resonance going on within the ring, but let's try to go outside of the ring, okay? Since we finished the ring. That's how I like to do these. I like to think of it as like different parts of the molecule and make sure that I don't forget one. So let's do red now, like this. So what we're gonna do is we're gonna take the original molecule, move this up here. I'm going to move that up there, get rid of the positive charge that is on that carbon, and move it somewhere else. Of course, everything else has to remain the same. Okay. So we move that bond down now, and so that means that the carbon right over here that I'm kind of highlighting, that is now going to gain a positive charge. Okay? Does that make sense? Now we can draw, is there any more resonance? I'm going to give you a hint. You have a little pair. Okay? So you definitely are going to want to use that. Okay? If you're, a lot of people we struggle with knowing how many resonance structures to draw. And do I continue or do I stop? Do I have enough? If you can, she is asking for the major contributor, right? So that means that there has to be one contributor that's different in some way. All of these have a positive charge on the carbon, right? So that's a little hint that you want to move that positive charge onto something that's not carbon to set it apart from all the others. Does that make sense? So we can move this lone pair, move it down, get rid of that positive charge, and displace it now onto the nitrogen. Hopefully I can fit this. So we moved it down, so that is the double bond that we just formed. And since the nitrogen now lost that lone pair, and it has 1, 2, 3, 4 electrons belonging to it, now it has a positive charge. So we moved it all the way until we got it onto the positive charge. So now I want to ask you guys, what is the major contributor? The nitrogen. First of all, it's the only one that's different. So if you're like unsure, like it's the only one that's different, so that's probably the reason why it's different, or why it's the answer. But the reason as to why, I know Miljonic sometimes will ask, like, why is this the major? And it's because, first and foremost, you want to fulfill your octet rule. Number 1, before anything else, you fulfill the octet rule. Whenever you have carbon with 3 bonds, it has a positive charge, like that. It's not fulfilling the octet. Does that make sense? It has 1, 2, 3, 4, 5, 6 electrons, not 8. Okay? And so all of those, all the ones with the positive charge on carbon do not fulfill octet rule, so then the one with the positive charge on the nitrogen, despite the fact that nitrogen is more electronegative, so you would think it's more electronegative, it does not want to bear a positive charge, but in the molecule, you are fulfilling the octet rule, and that comes before everything else, okay? So you would circle this one. You guys have any questions about that? Yes, you do. Sorry? Exactly, good question. So if everything had an octet, so basically, let's say you had a minus charge on a carbon versus you have a minus charge on an oxygen. Which one is more stable? The oxygen, because it's more electronegative. So both of these are fulfilling the octet if you were to count them. But the oxygen is more electronegative, so it is more stable with a minus charge. And it would be the opposite for positive charges. So if you have a positive charge on a nitrogen versus an oxygen, which one would be more stable with the positive charge? The nitrogen, because it is less electronegative than oxygen added with. Does that make sense? Yeah.
So we basically the way we answer this is by I guess in 2 steps. We get one positive to the nitrogen and the other positive away from the. So like the first step is you prove positive by making bonds, and so like we answer that step first to go back to the original structure and then the positive.
Yes.
So we wouldn't like answer it. We wouldn't continue proving the positive from the end of the first set of resonance structures. So like from the blue structure, we wouldn't continue from there, right?
No, you would not, because if you move, let's say you move that bottom bond, right, this way, then you'll displace the positive charge over, and now you're just writing the same thing that you had up there. You would have duplicates. Does that make sense? Yeah. Okay. Can we move forward? Also, yes. Intermediate. So these are resonance structures. So it's the same intermediate, but it's just resonance structures of that intermediate. So you don't have to. Okay, so for number 9, let's look at it. So circle the resonance contributors below and answer the following questions. Okay, so the first question says, write the hybridization of each atom indicated by an arrow in the box provided. Okay, so hybridization, we have our options of SP, SP2, SP3, and that's it. So we're going to want to consider resonance. Here, she gives you the resonance structures. But let's say she did not give you this on the right, then I believe that she would expect you to be able to draw the other one and take that into account. Okay? But she gives it to us, so that's really helpful. So let's look at the first carbon that has this box over here, okay? So you have one, and then if we were to draw this out, like H, okay? I just want to show you guys all the bonds. So you're going to have 1, 2, 3, 4 bonds, so what's the hybridization? SP3, is that what you said? Yes, exactly. So that would be SP3. You need to think of it as electron groups. You have 3 groups coming off of this carbon, or sorry, not 3, 4 groups, sorry, that's my bad. You have 4 groups coming off of this carbon, so that gives you 1s, 1, 2, 3p, sp3, that's how you do it. Make sense? Okay. And she showed you the resonance structure here. It's the same exact thing for that carbon, so that's why we keep it sp3 and move forward. Okay. So let's look at nitrogen B, for example. So right here, we have 2 groups attached to that nitrogen, so that would lead me to believe that this would be sp. S and P, that's why there's 2. However, I'm going to look over at the resonance structure that has been drawn. So basically, the resonance structure is showing that that lone pair, it comes down like that. Oops. I don't know why boxes come. Yeah, so it comes down and it pushes these electrons onto that nitrogen, and that's what's being shown over here. You see, that's the lone pair that's been gained, and this is the triple bond that's now been formed. Okay? So you just look at the resonance structure and you find the hybridization of that one. So we're talking about B nitrogen. So you have 1, 2 electron groups over there as well. So you're definitely going to go with SP. Does that make sense? So if the hybridization, if the resonance changes the hybridization, okay, you would go with the lower one as your answer. And hopefully the next question will have that. Yeah, the next question will have that, so I can explain that later. So let's look at C, for example. And what we have is we have 1, 2, 3 electron groups, right? So what would that lead me to believe?
SP3.
3 electron groups.
SP2.
SP2. Good job. So SP2, but let's compare it to after we did resonance in C. We have 1 electron group coming off from the left, this is the same nitrogen, and 1 coming from the right, so we have 2. So what would the hybridization be? SP. We go with the lower hybridization of SP. Okay? That's really, really key. The hybridization is not going to be changing because there's resonance. So it will take the lowest hybridization it can take because that is more stable. The higher the S character, SP, you have 1S, 1P, so there's 50% S character, that is more stable. So you would take that one. What's up?
So how do you change by resonance, how do you change the, you change it into a triple bond?
Yes.
No, wait.
Yes. So what happened was this lone pair right here, one of these, came down and it pushed this off because nitrogen cannot have 5 bonds. It can't be pentavalent. So it came down and formed a triple bond.
And then the double bond became a lone pair of that one.
Exactly. So that double bond moved onto this nitrogen here, giving it that second lone pair. Does that make sense?
Yeah.
Awesome. Okay, so we put SP for that. That looks good. And now let's look forward to the nitrogen over here, and let's count it. So here it has 1, 2, 3, 4. So that would lead me to believe that this is sp3. However, let's go back and look at our other resonance structure. and see how many electron groups that we have. We have 1, 2, 3. So sp2. sp2 is lower, so we're going to take sp2 and put that in our box. Does that make sense? Any questions about that? Always it's going to take the lower hybridization, okay? You solve for both of them, whichever one's lower, that's your answer, okay? Okay, so let's move forward to Na, Nb, Nc bond angle. So we're going to look at the middle atom. Our middle atom is the Nb right here. Right here. And we ask ourselves, what is the hybridization? We already determined it. It was sp. So what is bond angle for an sp hybridized nitrogen? 180. It's going to be fully planar. Both groups come up like this. Okay? That's something that I guess is just memorized. Okay, and then for C, are the p orbitals forming the Na, Nb, and the Nb, Nc pi bonds in the same plane? So with these, you could get into all the pi orbitals and how they look on the paper, but that's a lot. I'll try to give just a brief overview. Okay, so when we have hybridized orbitals, for example, let's give ourselves an sp2 carbon, okay? It means that it had 3 electron groups of some sort, so that's what we call the sp2. So here I'm doing like the x and the y axis of this hybridized orbital. And so you're going to have 3 sp2 hybridized orbitals coming off. And this is really hard to draw, so I'm just going to focus on the fact that if you have sp2, that means that you have 1 unhybridized p orbital. Okay? Remember, the highest you can go is sp3. Right? So if we have sp2, that means there's that 1 pi orbital that's not hybridized with the other, and it will look like that. Right? The dumbbell shape. So that will be your first one. Let's look at, for example, and these are the only ones where they could really ask this question. Let's look at if we had a carbon or an atom that was sp hybridized, okay? So that means how many unhybridized p orbitals would we have for that?
2.
2, very good. So because there's the sp3 would be your maximum, right? So those 2 pi orbitals are not being hybridized, so they are on their own. You have 1 pi and another pi, okay? Unhybridized. So let me just draw those instead of putting p. So you're going to have 1 that goes up, and then you're going to have another one. So you have 1 on the, what's this, y, and then you're going to have another one in the z. Like it comes right at you, kind of. Comes right at you at the plane. Okay? So let me go up and compare. So we're looking at p orbitals that are forming Na, Nb, and Nb, and Nc. So let's go back to our Nb right here and compare. Okay? So we said that our nitrogen A is sp2 hybridized, right? So that means it has 1 unhybridized p in the y direction. Okay? And then let's look at the atom on the right of the Nb, okay? That atom is the Nc. So we said that Nc was sp hybridized, okay? So that means that we have 2 unhybridized p orbitals shown here, and 1 is in the x direction, or 1 is in the y direction, and the other is in the z direction, right? So if you put these guys right beside each other, the y direction orbitals will overlap. You see that? They're parallel to one another. So if you draw this kind of like, they'll overlap like this. Okay? For example. But, so the Nc, it is sp, right? So it has that other unhybridized orbital, which is this one that I'm coloring now. The other one does not have that. So only 1 of these pi orbitals are overlapping. This on you guys' left, right here, it does not have one in the z direction. So because it does not, the answer is no. Because we're talking about plane, our plane is in the y direction, right? And in the z direction. They do overlap in terms of y direction, they're parallel. But in the z direction, one has pi orbital and the other one does not have. So long story short, you zoom in here, and you look at in A, because it said in A, and it said in C. So you look at in A. In A, my hybridization is sp2. In C, my hybridization is sp. They're different? The answer is no. Make sense?
So if one of them, if NA was, which it is sp2, and if NC was sp2, then they would overlap. But because they're different, they do not.
They do not. They only overlap with one plane, not the other. Does that make sense? I know that I think this was the trickiest question on this exam. My personal opinion, I think this was because this was my test.
Oh.
Yeah, this was when I took the, memories. So I remember this question, I had it circled. I was like, this is kind of this time. So, yeah, if they're different, yeah. Yeah, she's never asked that, other than on this test, I think. Yeah, I think. Because I remember looking at it and being like, I've never seen this before, and so I skipped it and came back, and I just guessed. I honestly guessed no shame.
So on a different test that I was looking at, they also asked something like this. They asked
Okay.
which molecules
Okay. So which molecules? Atoms. Atoms. So she was asking about which atoms are coplanar. So let's move just off to the side here. Coplanar, as the name says, it means they're in the same plane. So let's draw, for example, cyclohexane, our chair conformation. We have axial going up here. They're in the same plane. Those two are coplanar to one another. Does that make sense?
But I asked in my workshop, and he said like it was sp2 hybridized.
But the atom is coplanar. Maybe what they meant was, they might have meant this. So if you have an sp2 hybridized carbon, it's flat in the plane. So you need to imagine, like, is this the Mercedes sign or the peace sign? No, the Mercedes. Yeah, peace is like this, right? So it's the Mercedes sign. So it's gonna be 120 degrees each way, and it's flat in the plane of the paper. So maybe that's what he meant by it's planar. Yeah, that's really cute. Okay. Any other questions about that? What time? How are we doing on time?
20 minutes.
It's 8:40.
8:40. Let's see. If you guys have questions, the tutors are going around, so please ask them. Let's look at number 10. So arrange the conformations of 2, 3, 5 trimethylhexane in order of increasing stability. So it's really nice that she drew it out for you. She may just give you the name and expect you to be able to draw it. Okay? So just brief summary. This is not the molecule that is written here, but for Newman projections, you're just going to say that you have your eye is here. You see an eye? Zoom in. Sorry. Underwards. Okay, so is that better? So your eye is looking at it through here, right? So on the paper it's flat, but when you have your eye looking at it from that angle, what you have is one carbon directly in front of the other. So you're looking down the pi bonds, okay? Sir, what's your name? Can you help me? Not advertise, demonstrate? No, it's not bad.
I just stand up.
Yeah, you just stand up, okay? Yeah. What's your name?
Sergey.
well, I can't say that. What is it? Okay, this guy, my partner, my awesome partner. So imagine him and I are flat in the plane of the paper. We're like the molecule I wrote right there, okay? Now we're looking at it as though I'm in front of him and you're looking down me and him. Okay, I'm carbon 1, 2, 3. I'm carbon, if you count from right to left, 1, 2, 3. So I'm 3 and he's 4. My arms are the branches that are coming off and they're rotating like this. Move your arms. So then they're moving like that, okay? That's just basically in 3 dimensions. Thank you. Round of applause. You're awesome.
It's too kind.
Okay, so we're looking down it this way, okay? That is what Newman projections are. So I am this atom here. My friend was this one here. I'm gonna learn your name because I'm gonna get it right. Okay, clever this. And he's the big one in the back, okay? Little one is always the one in the front. Okay, so now we can rotate sigma bonds. There can be free rotation around them. So you need to keep one of them the same. If him and I were to move our arms the same way, we would be showing you guys the same thing. The same things will be back to back. So you want to make sure one person stays still and the other person rotates. Okay? So in this instance, we are keeping the front carbon still. You notice how this H is here, this H is here, this H is here, and nothing is changing and rotating? So we keep that still, and we rotate our back carbon. Right? So for example, what we have here is that this, what is this called, the common name, this group? Guys know? Isopropyl. There's 3 carbons, and they're coming off like fishtail, so it's isopropyl. And I'll show you guys a chart later. If you want one, I'll pull up a chart because it's really important, especially with helium. Meldonic hates nomenclature. So you're going to move this over, and that's what's giving you this. Does everyone see that? You rotate it one more time. That's what's giving you this. Everyone see that? Okay. So we are rotating them by 120 degrees every time, the back carbon. So how do we determine which one is the most stable? What is key is your bulkiest group, your heaviest group for each carbon. So you look at your front carbon and you say, what is my bulkiest group? It's the isopropyl. What is my bulkiest group on the back carbon? Isopropyl. Boom. They are 180 degrees. They are opposite from one another. So that is called anti. So that is probably going to be our most stable, but we'll look at the other guys just to make sure. Okay, here we have our isopropyl, back carbon, isopropyl. You see 60 degrees? They are much closer, so there's gauge interaction between them. That just means that theirs are so bulky. You have like 2 bulky people, or sorry, that's rude. You have 2 bulky groups, that was so rude. 2 bulky groups right next to each other. And so there's more electron repulsion. Does that make sense? More electron repulsion decreases the stability. Okay? And then here we have the same idea. You see how they're also 60 degrees? More electron repulsion. And then you're going to have to compare it to the next one. This also has a methyl group. Methyl group is not as bulky as isopropyl, but it is bulkier than hydrogen, for example. So that's, you're comparing these. Okay? So right away, my bulkiest groups on the furthest left one are anti from one another, so I'm going to put that as 3. And then right here, I have how many gauge interactions? 1, 2. 2 gauge interactions, that's going to put it as 2. Or 1. Sorry. And then this is going to be number 2, because there's only 1 gauge interaction. Does that make sense? Any questions? Yeah? Okay. Rotate the back carbon of the Newman projections above and draw the most stable conformation in the box. Or the least. I was like, didn't we just do that? Draw the least. Okay, so we're only going to rotate the back one, so let's just start off making our lives easier and draw the front one the exact same as it was shown. So CH3 with our isopropyl going up like that, and you can draw it in line angle if you want to. And then we have this like that. And so the least stable conformation is always going to be eclipsed. That means right behind one another, like the lunar eclipse or solar eclipse. But you guys know what I mean. So right behind one another is going to be the least stable. So that means I have a little group coming off from here, another group coming from here, and another one. These are directly behind one another, 0 degrees difference between them. I just have to show it like this so that they can see that I know that they're there, right? You're going to put the heaviest groups right behind each other. So we established that for our back carbon, our heaviest group was the isopropyl. So I'll put the isopropyl right here at the top, behind the other isopropyl. And then we look, our back carbon only has 2 hydrogens, so we have no choice, we have to put them right there. So that is our least stable conformation. Does that make sense?
So do you have to draw it like that, or do you write it out like CH, parentheses, CH3, parentheses 2?
Yeah. She asked if you can just write down the condensed formula as opposed to line angle, and you can. 100% you can. As long as you get the right number of carbons, you're good. Whatever you prefer, up to your preference. Okay, so now let's do chair conformations. Okay, so it's asking draw the more stable chair conformation for each of the substituted cyclohexanes shown below. It gives us 2. And so obviously each cyclohexane will have 2 different chair conformations, but here we only have to draw 1 for each. 1 for this guy and 1 for this guy. So if you prefer to go and draw the chair conformation one like this, and do the ring flip, so you're going to, like that, this comes here. If you prefer to draw both and then pick which one is the most stable, by all means do it. You do not have to. You do not have to. You can just think of it from the mindset, I want to draw the most stable, and so I will. So looking at the molecule that's on the left, okay, she is asking for the most stable chair conformation, okay? So when I'm thinking to draw the most stable one, I want to make sure that my bulkiest group is going to be in what position? Axial or equatorial? Equatorial. Boom. So I'm going to circle this, and I'm going to write that I want this to be equatorial, okay, when I draw it out. I'll draw out the chair. You can pick whichever one you want, whichever conformation you want, as long as you get everything right in the direction that they're coming off, okay? So when you're deciding on how to draw axial versus equatorial, some people get unsure of where to start. So I always like to say that every axial position, the vertex of the chair is pointing in the direction of axial. So if it's pointing up, for example, like this one right here, the axial goes up, okay? Equatorial is going to be opposite. So if axial goes up, our equatorial is going to go down like that, okay? If we move over to the next carbon, axial goes down, vertex is pointing down, equatorial goes up. And you fill it in as you go around the ring, okay? For this one, we're just going to fill in the carbons that have the groups coming off, so they don't get confused that we're drawing all these methyl groups coming off, okay? So what we have to do, okay, so wedge and dash are going to indicate up and down. They do not indicate axial or equatorial. So that is like a common thing. Up, and this will be down. It does not say anything about axial or equatorial, okay? Okay, so these guys, this is going up, the bulky group, because it's on a wedge, right? So I'm gonna make sure that I'm gonna put it on an equatorial position that is going up. So that's why I'm gonna start, this is my number 1, this is my number 1, they're analogous, and that is a 1, 2, 3, 4, so terbutyl group. So you can just draw it like this if you want, as a cross. You could draw it all out if you wanted to as well. So the other thing that's bonded to that carbon is a hydrogen. The hydrogen is going down. So if you were to draw it here, it is on a dash. It is going down in the space, and I made sure to have the iso, or not iso, terbutyl group going up equatorial. Yeah.
Well, you could number the chair's conformation
Any way you want.
It's like absolutely sure that you don't have to.
Yes, whatever floats your boat. Or your chair. Whatever floats your chair. Yeah, you can do it anyway as long as you're consistent though. So if I'm going to start, this is my number 1, and I go 3, 4, 5, 6, right? Then I'm going to make 2, 3, 4, 5, 6 like that, right? Whatever is on my third carbon up there should be on my third carbon on the chair conformation. Okay, so I'll draw whatever is going down like that. Axial goes down, equatorial goes up. And so what is coming off of my third carbon? An ethyl group, it is going up. So that's why I put it up. And it happens to be equatorial, which is good in terms of stability. And my hydrogen goes down axial. Okay? And then let's move forward to the number 4 carbon. You'll have axial points up like the vertex, and then you have your equatorial pointing down and pointing down. So your CH3 is going up because it's on a wedge. So I will put it up, which happens to be axial, and my hydrogen is shunt. Okay? So that's how I would show this chair conformation. Now, if I were to have done the ring flip for what I do on the page, everything would swap in the sense that it would still be up and down. Everything that was up will still be up. Everything that was down will still be down. But what is different is that, for example, this iso, or not iso, terbutyl, this terbutyl here, it would go axial. Okay? It would still be up, but it would be axial. So that's why I put the most stable one here, going equatorial. Yes?
On the test for Bean, do you know if she minds if we draw it out, or can we write CH3, CH2?
You can do either one. Yeah, whatever you want, as long as it's the right number of carbons. Yes. You'll get full credit both ways. Yes?
Why wouldn't you start numbering from the methyl?
You can start numbering from the methyl if you wanted to. You can number it any way you want to, as long as you're consistent. Your number 1, if your number 1 is the methyl, that has to be the number 1 that has the methyl. Yeah, they have to be the same distance from one another. Like this CH3 is 1 carbon over from the ethyl, so in your chair it should be 1 carbon over. Does that make sense? Yeah, so that's a really good point actually. So what's bulkier, methyl or terbutyl? Terbutyl. So that's your priority. Like if you had a conformation that showed you 2 methyls, axial, but your bulkiest group, the terbutyl, was equatorial, that is the more stable one. It takes priority. That's why I numbered it as number 1, just because I wanted to remember to put equatorial. Okay, any other questions, or we can move to the other one? Okay, so the other one is the same idea. Everything is just now going down in the plane. So I'm just going to draw the chair conformation for this same idea. I'm going to draw it like the same, in terms of ring flip, it looks the same, just to help you guys see it in comparison to the other. And so we are eventually going to be looking, it wants the most stable one, so I'm going to look at my terbutyl group, and I want to put that on equatorial, okay, right away. And I need to make sure that it goes down in the plane. So if this goes up, right, because it goes with the vertex, that means the equatorial on that carbon is down, okay? And I want that terbutyl to be on equatorial, so I'm purposely writing this conformation to put it on equatorial. So I can draw it, I'll draw it as you were asking. Can I draw it this way? Tree like that. Does that make sense? I heard an O. I heard a really loud O. That's good. No reason to have it. Okay, and then that means your hydrogen is going up. Okay, so let's mark that as our number 1. And then you can number it any way you want around the ring. Let's just do it 2 like this. 3, 4, 5, 6. And then we'll go 2, 3, 4, 5, 6. So at our number 3 carbon, you have the CH3 it's going down in the paper. Remember, axial is up. Equatorial is going down for this carbon. So it's going down, so you have to put it equatorial going down. Make sense? And then the hydrogen. Okay. Now let's look at our number 4 carbon. Axial pointing down goes with the vertex. Equatorial is going up because axial is going down. They're always going to be opposite. So then whatever's going down is your ethyl groups. I'm going to put CH2, CH3 going down. It is axial. Okay, and then we have a hydrogen going up, but it's equatorial. So now we have drawn both our most stable chair conformations. Any questions? No? Okay. So now we're going to ask yourself which one is the more stable isomer. So these have the same condensed formula. They are just in different orientation in the space. So we're going to compare and see which one has the bulkiest groups on equatorial. So if we look at the left one, we have the isopropyl, or tert-butyl. I keep calling it isopropyl. So the tert-butyl and the ethyl group, they are both equatorial. Our methyl group is axial, so we have 2 of our bulkiest on equatorial. And then if you look at your right one, whatever you have equatorial, which is good for your tert-butyl, but then you have your second heaviest group is axial. So that's a problem. Even though the methyl is equatorial, you look at your 2 heaviest. So this one has the CH3 in the axial position. So which one is more stable? A or B?
B.
A. Oh, you say B or A? Okay. So let's look at A one more time. So we're looking at the tert-butyl group, right? And we're looking at the ethyl group. Those are the 2 heaviest groups. Both of them are equatorial. That's what we want. That is more stable. They're going out, like the equator is horizontal, so they're going out, and they're not having steric hindrance. There's no crowding of the electrons and repulsion. So we have 2 bulkiest groups on equatorial, so that makes it a more stable isomer. Okay. And if you have any questions, please ask Chance. For the reactions below, provide the curved arrows to indicate the flow of electrons associated with bond breaking and bond forming. In other words, provide the mechanisms. So in class, I don't think she's gone into mechanism yet, but she probably has done free radical halogenation. That is the first reaction from order 1. As the name says, you're going to form free radicals. Free radicals means that you have an atom or molecule that has one unpaired electron on it, such as this bromine free radical, okay? That's, as you're going through the reaction, you get that as your intermediate. That's what that means, okay? So for doing these, you really just want to compare your reactants and your products and see which bonds have been broken and which bonds have been formed. So let's compare, for example, this right here with this. And we can see that this bond with the hydrogen was broken. Okay? And then we can see that the hydrogen bond was formed with the bromine. When I say a bond with hydrogen, not hydrogen bond in terms of intermolecular forces. So I know that that breaks. So with free radicals, since you have one electron only, it's not a lone pair, you do it as half-headed arrow, not double-headed. This is the only time where you will show arrows coming and meeting halfway. Okay? Normally, it's double-headed arrow, it goes all the way, it abstracts a proton or attacks something. So here, if one of these electrons is going with the bromine, then the other one is coming back onto the carbon like that, and that's where we see this unpaired electron come from. Does that make sense? Now we form the bond with bromine, that's how you get the HBr. So you would draw it exactly like that, meeting in the middle, and that's it.
If it's only one electron, then they would meet midway.
Exactly, yeah. So you see how with HBr, there's 2 electrons, 1, 2. That one is coming from this, and one is coming from this. The other one in that bond goes on the electron. Okay? Okay, so let's look at B. Let's same process. So here we have the oxygen with a positive charge that has 3 methyl groups attached, versus on the other side, you have this ether. So that just means oxygen with 2 carbons coming off, and it no longer has a positive charge. So it must have gained electrons in some way. So that means that there was a bond that was broken in order to form that. This bond must have been broken. Okay, you see how it's gone? And it was there, now it's gone. And then what was formed on the other side, we can see that you have this OH that is analogous to this OH. What bond was formed was the one between the oxygen and the methyl group. So that means that kind of makes sense, because we said that this bond is breaking, so this CH3 is probably going to form a bond with something else, and that's the oxygen. So when we're trying to show the arrows for this, you circle the lone pair on the oxygen, and this is going to go and attack something, double-headed arrow. Now what is key is that commonly whenever you see an oxygen with a positive charge on it, remember how oxygen is very electronegative? So it is extra unstable with a positive charge. It already wants electrons, and now you're calling it electron poor. You know, you're taking away those and you have a positive charge. So that means via this sigma bond here, oxygen is pulling electron density towards it. So that makes this carbon a little partially positive as well. It kind of follows through like domino effect. This comes here, attacks that carbon. This bond that I have everything drawn over goes to the oxygen. Okay? So this right here, this oxygen that I'm circling, is now connected to the CH3. That's right here. Now that oxygen lost that lone pair because it formed a bond. And so that's why it gets the positive charge now, because it lost that one electron. And then this right here, it gains electron pair, that's this electron pair right there. So it becomes neutral.
I understand that the electron from the oxygen goes to the other side, but how do you know which of those it goes to?
Like which oxygen gains the CH?
Which of the, I mean the arrow is pointing towards the methyl group, so
yes.
I know which one.
So your arrows show you the bond that is forming. So this arrow that I'm highlighting, that is the bond that is forming between the oxygen and the CH3, which is right here. You can think of it as that is your bond. So we're using 2 electrons, so it's 1 electron pair. Yeah, it's 1 electron pair versus up here it was just an unpaired electron. Okay, let's move forward to C. So C is similar in a sense, and also another thing with orgo is that whenever you have different charges, negative of course likes to attract the positive. So the negative, the atom that has a negative charge on it will be able to use its lone pairs to go and attack something. That's a common trend that you're going to see. So if you were unsure of how to start with this, you can look at what is negative, what is positive, something's going to happen there. That's where the reaction is going to take place. You always show the arrow going from the electrons, not from the atom. So that's how you would circle this lone pair, and it needs to go and attack something. Now we need to look at this molecule and see what bond was broken, not formed, broken, in order to give us the product. So we have this ring opening, in a sense. You have this ring opening, and the iodine, a lot of people miss this, I think, on this here. They would show the iodine going and attacking the oxygen. But in our product, is the iodine attached to oxygen? No. So that's super key. You have the same thing as I was kind of showing with the previous problem, I'm going to zoom in a little bit, is you have this electronegative atom with a positive charge. It really wants electrons. So it is, via the sigma bond, pulling electron density towards it, making this carbon partially positive. So that is the site of attack of the iodine. So that comes here, attacks that carbon, and this leaves as what we call a leaving group. As a leaving group goes, it leaves. So that's how you get this. It opens it up. And you can see how those electrons in that bond go to the oxygen, so that's how you get the lone pair here. And then the iodine is now attached to it, like that one. All right, is that it? Is that it? That is it. Okay, any questions about anything?
Propagation.
Propagation? Okay. Any questions about this exam in particular, though, before I exit? No? Okay. Thank you guys so much for coming. Best of luck to all of you, and I hope we'll see you tomorrow. Chance will be leading the whole thing, and I'll be walking around. But thank you so much for coming.
The saturated
Are we using or? I don't know. Is it?
Saturation number is basically whenever you have a saturated molecule, all the spots with carbon are saturated molecules. They have a maximum protected bonds to it. So, it doesn't have to do with polarity, but what it does